We have got a lot of questions where we're going to be, well, not a lot, a few questions, but they're going to take a lot of time. Oh, hold on a second, get someone in chat. Let's see what they've got. Okay, that's good. So where was I? Yes, we're going to look at what's called Stokes' theorem. And the majority of the questions are all the same, except for the first one in the homework, just to show you. And we're going to be looking at essentially how to find a line integral in terms of a surface integral, which then turns into a double integral. So it's a bit like you're trying to get A, but you don't get it directly. What you do is you find B, and then B allows you to get A. You might say, well, that seems a lot of work. Sometimes a line integral is just impossible. I mean, the integration just doesn't work. You can't do it. Or it's very, very difficult because it breaks into so many weird parts that you can't do it. And you might not believe me, but Stokes' theorem, although it's very long, most of the questions are quite long, does allow you to find the answer to quite complicated line integrals in particular. So the motivation behind it is Stokes' theorem is meant to be a way to find line integrals rather than just doing them directly. So first thing I'm going to do then is zoom over, hopefully, to, I believe it's, now I'm going to try and find out what the screen is. I believe it's this screen here. Are you looking, you know, the usual question, are you looking at a screen that says Stokes' theorem? Is that what you can see as your main screen from me? It says Stokes' theorem.
Yes.
Yes?
Yeah.
Perfect. Okay. So I have made up solutions to 6 out of the 7 questions, and we're going to go through them. This will be turned into a PDF once I've got as many of the usual typos that I made sorted out, and as soon as I finish the 7th one. So there are only 7 questions in Stokes' theorem, so you can imagine there must be a lot of work in them for just so few questions. So let's show you what it kind of does. Let's see if I can zoom this up a little bit. Suppose S is a surface, so that's that blue, light blue surface, that's S. And they talk about a normal vector and positive orientation. And through this thing, there is a vector field passing through it. And we would like to calculate the line integral going through S and the vector field. So basically, we're being asked to find this integral here. Well, Stokes' theorem says that this integral can turn into a surface integral over the surface S. So you have a line integral which is boundary of this. S is the inside, the surface, and this line integral can be found by finding the surface integral of the curl of F ds. F is going to be called PQR. The curl of F is this fella here. And there is an alternate version of Stokes' theorem where it's not really used so much, but you can use it to find the integral of this surface integral and convert it into a line integral. But for the most part, Stokes' theorem is used to take line integrals and reconfigure them into an equivalent double surface integral. So this might be almost impossible or virtually impossible to do, but this fellow over here very often is a lot easier to do. And you're going to trust me when I say that that's the case. So let's jump right into it and show you what it looks like in practice, because I think it's one of these things that you get more understanding once you've seen them. So this is a version of question 1. This is us going to use Stokes' theorem in the less common format. We're going to use it to find the double integral of the curl of f ds, which is this fella. Now f is given as this ugly function, and the surface S is a hemisphere, right? So half a sphere. There's the sphere's equation, and y is going to be greater than or equal to 0. So if you can visualize that in 3D, it's not the top half of a sphere, it's like the right-hand side of a sphere. So imagine the sphere being cut vertically, and you're only looking at the surface generated on the right-hand side. So that's a little bit different orientation. So according to Stokes' theorem, a double surface integral of curl f ds is the same number as the single line integral over C of f dr. Right, so first we have to figure out who C is. Well, C is this sphere intersecting with y equals 0. And what that gets you, if you make y 0, what that gets you is that C is x squared plus z squared. So can you imagine that's a circle, right? And since y is missing, do you understand that's basically going to be on one of the side planes? So can you imagine that half sphere I'm talking about? If you projected it onto the side, it would be a circle, and the circle would have this equation. So what I'm going to do is I'm going to take the line integral using this fella here as my curve and converting it into parametric form. And here's our first little, oops, let me fix that. Here's our first little issue. If you want to turn this into parametric form so that you can find the line integral, then you have to realize that for a circle, x is 5 cos theta, making y 0, right, because it was cut at y equals 0, so y is always 0. And z is 5 sine t. That will generate this curve in 3D space. Now, it's x and z this time. That's why this guy's cosine and this guy's sine. And this little weird thing at the end, I wish they didn't have it, but orientation is important, and you always want the thing to be a positive orientation. So basically, I'm just doing it from 2 pi to 0 rather than from 0 to 2 pi. That's so I go round the curve in a anti-clockwise direction. You know, if you go normally, you go clockwise, but if you do it the other way, you go anti-clockwise. So that's what that weird thing is, and I wish it wasn't there, but it is. So back to our problem. We have a line integral. What does the curve look like? In parametric form, it looks like that. What does the vector field look like? It's got this equation, but every x is going to be turned into 5 cosines, and every y is going to be turned into 0, and every z is going to be turned into this fella. So that guy, and that guy. So the function f in parametric form using t as that guy. Since this is my r of t, the derivative of it is this guy, 0, this guy. So that's where that comes from. And so here we are. Original question, find this surface integral. Turn it into a line integral that's got the same value. That's what Stokes' theorem says you're allowed to do. That particular line integral is going to be over a circle. That fella there. This function here is f converted into parametric form. Dot product with the derivative of r, which is that piece, dt. So what I've essentially done is I've taken this line integral, parametricized it, and now it's all in terms of t. Now you may have to go back a little while till you did some of the line integrals, but in some of the line integrals, couldn't you turn everything into t's and differentiate it? And then integrate with respect to t. So that's what I've done here. If you follow through the lines of working, basically when you multiply things and add them together, that's the only guy that lives. And then I've done a little trick. You remember that weird order that I made t go so it would go round anti-clockwise? Do you know in integration, if you switch the order of integration, you make it negative? So the integral from 2 to 1 is the same as negative the integral from 1 to 2. I'm using that property. So that's where that weird negative came from. And if you multiply these together, you get that in 2 zeros. This integral here turns into that one. Now, at that point there, I've given the rest of the details, but essentially the original integral, this surface integral, was turned into this guy here. And we know how to get that. It's a Calc 2 question, and there's a whole load of work in, but eventually it's 25 pi. So if you're ever asked to find a surface integral, and you're being asked to use Stokes' theorem, you're going to turn that surface integral into this guy over here, line integral. And then you're just going to work your way through it, probably using parametric form. That is a very rare version of how Stokes' theorem is typically used. You don't normally get a surface integral like this and asked to calculate it. What you're more likely to get, and almost every question after this is like this, is that you're going to be asked to find a line integral. Right, the classic line integral FDR, right? Now, what does Stokes' theorem says? Well, it says that thing can be turned into a surface integral. Well, let's see what we have. We have a vector field F, which is given by this, and we have the C, which is basically the path, and it's a triangle, and these are its 3 vertices. So if you imagine drawing that triangle in 3D space, it would basically be a little triangle wedged in the corner of the XYZ axes, right? Up at 9, down at 9, oh, cross at 9. You imagine that little triangle? That's what that C would be, the outside of that triangle. So according to Stokes' theorem, if you want to find this line integral, you can find this surface integral here. That means I'm going to have to find the curl of F. In this question, the plane was formed by passing through these 3 points. Now, I've skipped a whole line of work in here, but do you know if you know 3 points, you can find the equation of the plane that passes through them? So that fella, x plus y plus z equals 9, is the surface that we're going to need for the surface integral, right? It's basically a big triangle. Now, F is given by this. I'm going to call the first guy P, the second guy Q, and the third guy R. So far, so good. Now, to get the curl of F, you basically do IJK, delta, and PQR, right? It's this cross product. And if you cover this guy up, you get these guys. You cover the middle one up, you get these 2 guys. And you cover the last one up, you get these 2 guys. So, for instance, the partial derivative dr by dy. This is r, and its partial derivative with respect to y is 0, so that's where that came from. If you want to get the partial derivative dq by dz, then q is the middle one, so it's this guy, and you do a partial derivative with respect to z, and that's where that came from. So 0 take away 2z, for example. Now, if you go through the other 2, you get this, and the third 2, you get that. So we've now got the curl. It's this fella. So this integral has now become this integral. And I've decided to call this guy, the curl of F, for convenience, I've decided to call it this guy G. So that's going to be a typical process. So let me wind back and talk about what that typical process is going to be. We're going to have to find, or be told, hopefully, what the surface S is. We're going to be told F. We're going to find the curl of F. And the answer to the curl of F, we're going to call it G, right? Just as a placeholder. Now what's going to happen? Well, according to this theory up here, won't this fella equal to that guy? So the integral of the thing we're wanting is the same thing as the integral of this surface integral here. And this is G. So what's the next phase? We need to find this guy. So we didn't get the answer right away. What we did is we took the fella and we turned it into a surface integral. We're now going to take that surface integral and find what it's equal to. But if you have any experience with surface integrals, most of them are horrible to do if you leave them as a surface integral. What you typically do is you use this weird formula here, which takes surface integrals and just turns them into good old-fashioned double integrals. You know, the ones that go 0 to 2 and 5 to 9, if you're lucky, right? Or 0 to 2 and y equals x to y equals 2x, right? That kind of shape to them. And this is a standard formula. It's true every time. And it says that this surface integral, or any surface, can be written in this format as a double integral. So pause for a minute. What we've done here is quite messy. We started with being asked to find a line integral. We converted that into a surface integral of this guy here, the curl, right? And then we've taken that answer, and now we're converting that answer into a double integral. So it's line integral becomes surface integral, which then becomes a double integral. And then you've got the answer. So it's quite a long road. So right now we're halfway through. And I'm saying that if you want to find this surface integral, you use this ugly guy here. Now P, Q, and R are this guy, and this guy, right? They're just placeholders, right? P, Q, and R is shorter than, you know, as a general version. And who is this D? When you did surface integrals, don't you project the surface down onto the floor, right? So when you do that, that's who D is. Now, if you look at the question that we've got, and we're trying to take this surface and drop it down, what we've got is the x plus y plus z equals 9. That's that sloping plane, right? And it's only within certain regions. If that drops down to the floor, you'll find that all you need to do is basically make z 0, and that's what it looks like on the floor. Right, so you see this sloping line, its shadow on the floor is basically just this fella, which if I rewrite it is this guy. So this plane has this image on the floor. Y equals the straight line 9 minus x in between 0 and 9. So we have all the pieces that we need. We know what the projection of S is onto the floor. And we've got all the P, Qs, and Rs that we could possibly want. And Z, well, Z's the equation of the plane, but it's been rewritten in the format Z equals rather than the original format. Right, so you plug in P, you plug in Q, and you plug in R. Then you do the derivative of Z with respect to X, which gets you what, -1. The derivative of Z with respect to Y also gets you -1. This guy here doesn't have anything, it's just R on its own. Combine all those terms, tidy them up, and you get to here. Now you can see we've at least got a double integral, and we've got boundaries that are reasonably nice. There's only one fella left to take care of. See that Z that's here? Because there's very often going to be some Z's left over. We need to figure out how to replace him in terms of X's and Y's. And that's who we use here. So if there are any Z's left over, whatever this Z here is, gets placed here. I'll multiply this all out, and almost like magic, there's our integral. So the original line integral, which was virtually impossible to do, has now turned into a really quite a baby looking double integral. And you go through all that working, it ends up being -729. So we were being asked to find this line integral. It became this surface integral, which in turn became this surface integral, which in turn became that guy. And I'm going to have to shrink this up a little bit so I can get it all to fit. This is what's going to be turned into a PDF, and you'll be able to actually see all this. So you don't really need to spend any time trying to frantically write. And hopefully you can just watch. Now, what we're doing here before I move on is quite high level math. What you're looking at is how does a mathematician approach a problem that there is no direct solution to? Can you imagine that this guy here, this line integral, was just not possible to do, right? The integration was just, it's like trying to integrate e to the power of x squared, right? You can't do it, right? Just ain't possible. So you had a question you don't know the answer to. So what did they do? Well, they turn it into something else that they know the answer to. If they don't know the answer to that and it's quite difficult, then they turn it into something else. If they don't like that, then you turn it into something else. In Stokes' theorem, this is the pathway that you use all the time. Your line integral will become this ugly surface integral, which is basically the same thing as that guy, which then turns into this double integral. So as long as you have that process in your head of A to B to C to D, you're going to get the guy. But you can also see how much work there is in that guy. Okay, I'm ready for some questions, including screams of, that's impossible. It's not. If you do enough of them, it is possible, right? Have we got any questions?
I have a question on the first one.
First, okay, let me go back to it then. I should have probably not left in the first place. Right, this first one is a very special situation. It's the atypical way of using Stokes' theorem. You don't normally do it this way. Right, I'm back to one. I hope I'm back to one. I'm probably not back to one, am I? We're on the piece of paper. Right, let me try that again. Right, I should be back on one this time. Can you see it?
Yeah.
Right, yes.
The question's pretty simple. Why are you making y 0?
Oh, okay. Right. You see this bit here where y is greater than or equal to 0?
Yeah.
Right. And imagine this is a sphere, right? And then you have y greater than or equal to 0 is you're cutting the sphere and then taking everything on the side that has a y coordinate of greater than 0. When I try and find what the curve C is, I'm trying to find where this fella, right, the x squared plus y squared plus z squared, which is a surface of a whole sphere, meets up with the slice y equals 0. So I'm picking y equals 0 because that's the boundary of the entire region. So if they had said y is greater than or equal to 2, I would have solved this by making y equals 2, and then I'd plug y equals 2 into here, and that would have generated what the shape would look like. Actually, it would have just been a smaller circle.
Oh, okay. All right, thank you.
Right. You're probably only going to get one shot of this, so that's it. So it's not something that is typical, right? Is there any other questions on those couple of examples that we've just done? Okay, so I'm going to show you, I'm going to talk through at least another example. And I hope by the time you see 4, 5, and 6, because that's probably all the time we'll have after this, maybe not as much as 6, you'll see that there is a process going on. It's do this, then do this, then do that. And if you can keep that process going, although they're quite long, at least it's a process, right? It's something you can learn to do. So here's the next one. Use Stokes' theorem to get the classic line integral. C is the usual go the right way. Here is your vector field. And C is the boundary of the parts of the plane 3x plus 2y plus z equals 1 in the first octant. Okay, you know how we have quadrants 1, 2, 3, 4 in 2D? Do you know octants are used in 3D? And do you know the first octant is the place where x, y, and z are all positive? So you can imagine in 3D space the x, y, and z having planes through them. Can you see why there'd be 8 little cubes? They're called the octants because there are 8 of them. And octant 1 is everybody positive. Right, so that's what that was about. So let's see what we have. Well, we're going to use Stokes' theorem. Stage 1, let's find the curl of f. Right, the surface integral, the curl of f. So this is f. So we'll call this guy p, this guy q, and this guy r. And here is the curl of f. And can you just trust me, which is dangerous, but I believe it's right, that eventually you get this guy here, right? You can look at these notes when you've got time. So, happy? Here's f, now I've got the curl of f. So that guy there, I'm going to call him g. So this fella, this surface integral, can also be written as this surface integral, right? It's just convenience. So line integral has now been converted into surface integral, this one here. The next phase is to find out what the surface integral is equal to. Well, the surface integral gets converted into a normal, good old-fashioned double integral. You know, the 0 to 147 thing. Now, to be able to do that double integral, we need some information. We need to know who d is. So that means you have to think, what does this surface look like when you project it down onto the xy plane and you restrict yourself to the first quadrant, right? Because the first octant will become the first quadrant when it goes to the floor. And so all I'm going to do here is take the equation of the plane, which is this guy, rewrite it as that fella, and that means I now know who z is. I need that because these guys are going to turn into x's and y's. I also need to know what d is. Well, if you take this fella and you make z 0, that's how you get the projection on the floor, right? It's what the thing looks like when z is 0. And that turns into eventually this, which I'm now going to rearrange as that. Now there's some bits missing here, but can you imagine drawing the line y equals that? So it's a diagonal line. And basically it makes a little triangle. And the triangle goes from 0 to 3 on the x's and from 0 to a sloping line on the y. So you can imagine the classic little right angle triangle thing that you typically get. If I had time, I would have put that picture in, but then that would have added another half hour onto my workload. Are you comfortable about how we took this plane and figured out what d is? Make z equals 0, and then you've got a two-dimensional area called d. It's a little triangle. And so this fella becomes this guy. That's what z's going to be whenever it appears. This is the range in y's. This is the range in x's. So you can see 0 to y, x is 0 to 3. P, Q, and R. Well, P is this guy. Q is this guy. And R is this guy. So if you're wondering where P, Q, and R came from, they're this one, and this one. P, Q, and R. They've got dz by dx, dz by dy. You get them from this fella, right? The equation of the plane. Right? If you rearrange the equation of the plane in the format z equals, it looks like this guy. So if you're wondering where dz by dx is, it's this derivative, and that's where -3 came from. And dz by dy is this guy with respect to y, and that's where the -2 came from. So you tidy this all up, and you get this fella. Now, in this particular question, we kind of got lucky. Although it looks like I could have probably done another line there. Let's put that line in. I need some space here. Can you bear with me for a few seconds? I just realized. Oh, didn't mean that. This could be tidied up just a tiny little bit. Yeah. So that is the end of the line. That is the double integral that you always end up with at the end of a Stokes theorem question. You start with a line integral you can't do, and you end up with a double integral, a normal good old-fashioned xy or sometimes polar double integral. And trust me on this one, I believe it's 1/24. Now you see the beginnings of a pattern here. Line integral becomes a surface integral with a curl being used. That surface integral eventually becomes a good old-fashioned double integral, and we're ready to go. So here's our next fella. The classic line integral again. Z is, they're calling it a paraboloid. That's nice. It's basically, do you know one of those little curvy things that go up in space or curves down in space? I think this one's more like a hat, right? It comes down the way, like a dome. And we're being asked to calculate the line integral. And they're talking about the first octant again. In other words, x and y are both in z. They're all positive, right? So x is greater than 0, y is greater than 0, and so is z, right? So it's only this surface if you dropped it down and hit the first octant. So here is f. We'll call it p, q, and r. Here is the curl. Usual process. Can you trust me? That's what you get. So this guy I'm going to call G because that's just the way I'm doing this. The one example, there might have been two, the two examples in the textbook that I saw skipped so many lines that it really was almost impossible to see where things came from. They just went from line 5 to line 15 as if it was obvious, right? So I've probably put more lines in than you need. You know, when you're doing your own working, you might say, I don't need to put that line in, I can do that bit in my head, and that's fine. But at least I'm showing you everything, maybe even overkill on it. So anyway, that's this surface integral, which becomes, for convenience, this fella. So that's going to be our G. This guy's going to be turned into the classic normal double integral. So to have all the pieces, well, P, Q, and R, right? Got him. Do I have the surface Z? Yes, I do. Z is this guy, right? I didn't need to calculate him, right? It was staring me in the face. That's going to be the Z. That's going to contribute these pieces here, right? And it's also going to contribute, if there's any Z's left over, then I can turn them into this 1 minus x squared minus y squared when I do my double integral. So the only thing I've got left is, what does D look like? So you've got to imagine that you took this surface here and you projected it onto the floor as a shadow. Now, how do you do that? You just make Z 0. Can you see that becomes x squared plus y squared equals 1? So if you make Z 0 and you tidy it up a little bit. So it's a circle. Ah, but wait a minute. Is it the whole circle? Or was there some restrictions on it? It was in the first octant. When you drop that on the floor, doesn't that become in the first quadrant? So that means I'm only doing a circle from 0 to ½ pi. So if you're wondering, I went polar on you, right? So if you're wondering where 0 to ½ pi is, that's where that's going to come from. So here goes. This surface integral becomes the typical double integral formula. If you plug in all the bits, you get to about here. And then what I did is I kind of earlier on looked at the information and I'm saying to myself, do you know what x squared and y squareds and half circles and quarter circles and stuff like that? Doesn't it make you think polar? So I'm not going to do the dA converted x and y. I'm going to do the dA converted as r dr d theta, right? I'm going to do polar on it. So I'm still got all my x's and y's, and I get to about this line here, right? And then I'm beginning to nibble at it. Do you know that x squared minus y squared gives you this 1 minus r squared? 2xy becomes 2 this guy, that guy. Remember, x is r cos theta and y is r sin theta. This fella here becomes the 2r sin theta. This little x becomes that guy. And then you have an r dr d theta to tag on. So essentially, I've taken my double integral and converted into a polar version of itself. And it is one ugly looking polar integral. And I would guesstimate there's probably about 8 or 9 lines where you have to fight your way through it. But you can do polar, can't you? You can just, you know, sines get you in negative cosines and r cubes get you a quarter r to the 4, right? You can do it. Just really big and really ugly and really long. And I didn't have the time or patience to do it all, so I just told you what the answer is, at least for this particular example. So the original line integral became this surface integral, which is essentially that same surface integral, which became that guy. So I guess I should put that in for completeness sake. Have you noticed that the last 3 questions were pretty much identical in process, right? What I did was the same. The mechanics were different because different functions, you have to deal with them algebraically different, but the mechanics were pretty much the same every time. Okay, time to pause because I know I've put a lot out there. Any questions? Do you feel comfortable that if you spend some more time after this lesson and you go and look at my notes and so on, that you'll be able to do a question like this on your own? Right, the kind of the A, B, C, D stage. So we've got time, I believe, look at my clock here, we've got time for, we'll see. Definitely one more, maybe 2 if I'm quick. Classic question, find a line integral. This time it's the intersection of this plane and this cylinder. So this one has given us a little bit more work. Essentially what we're going to have to do here is at the end, aren't we going to have to find out what do these 2 things intersect at? They're going to intersect at some kind of curve. And then that curve is going to be projected onto the floor, because that's going to be D, right? The shadow on the floor. So I know eventually that's where I'm coming from. But before we get to that point, let's get the other stuff out of the way. So I'm going to use the curl F version. Here is F. Here is what the curl looks like. A pretty nondescript curl, right? Nothing too messy. So that means that G is going to be this guy. So we're now going to be turning this surface integral into this guy. And G is this fella. So that's going to be P is this guy, Q is -1, and R is Z minus 3. Pretty standard. So where's the hard work happening? Right now. The D is going to be what you get when you intersect this plane in 3D with this cylinder. Now this cylinder is easy. Can you imagine x squared plus y squared plus 1 being a cylinder going vertically upwards, radius 1? Can you imagine what z equals y plus 7 would be like a slice, like a plane cutting it at an angle. Now I can visualize that. That would be an ellipse, wouldn't it? right, the C. Take a cylinder and cut it at an angle, look at the intersection, that would be an ellipse, right? The C would be an ellipse. If you take an ellipse and then you project it down onto the floor, that's the D that we need to find. Whew. Okay, so what does that D look like? The good news is it's going to look like x squared plus y squared equals 1. And I did that because I can visually think of it. Can you imagine the cylinder going up the way? When you cut that shape, won't the projection down to the floor still be the cylinder, the circle part? X squared plus y squared equals 1. So we got lucky, right? The D was not that hard to do, but I didn't do it by math. I just visualized because I saw it, right? I saw what that was going to look like on the floor. So I see this guy, and I hope you see this guy and you think, polar, right? X squared plus y squared, polar. Much easier to do than x's and y. So this is another polar one. So this surface integral gets converted with its typical formula. There's P, there's Q, and there's R. dz by dx is this guy's derivative with respect to x, which is 0. And when you do it, you get this fella. Well, that's a bit messy. Do you see how you get a z here left over? Well, don't you just go back here and make the z y plus 7? So here's, I think this is the first time we actually got to do it. Now, if you make that y plus 7, and then you add 1, that's 8, then you take away, you get 5. Can you see where that came from? Now, I'm going to go polar. That means the y gets turned into r sine theta. The dA becomes r dr d theta. And it's a complete circle this time. So 0 to 1 and 0 to 2 pi. And trust me, the answer is 5 pi. Are we seeing a process? Line integral, surface integral with curl, turn it into a surface integral with a big G, turn it into a good old-fashioned double integral. Either go X, Y, or polar, depends on what you get. Side jobs, you need to know who D is at the end, don't you? You need to know what the shadow of that entire surface is on the floor. And we do have time for the last one. Well, the last one I've got notes for. I'll be doing 7 after this. Now, a particle is moving along this line segment from the origin to here, to here, to here. Now, this is jumping ahead a little bit. If you plot the point 0, 0, 0 and all the other ones in 3D, you basically get sloping thing. But what is good is, if you take that shape, because it's basically like a rectangle on its side, right? Because it's a boundary, right? You're going from this point to this point to this one to this one, right? It's a boundary. If you take that shape and you project it on the floor, because remember the bottom line is we need to know D. I don't need to know all the bits that get you to D as long as I can get to D. In this case, don't you just make everybody's 3-dimensional coordinates become 2-dimensional? In other words, remove the Z value. And if you do that, do you know this guy just becomes a rectangle? So bear that in mind. The D is just going to be a rectangle. So we're going to do this guy becomes that guy. Here is F. This is what the curl of F looks like. So we're going to take this surface integral, rewrite it as a surface integral with G, and this guy is our G. Then we take this fella and we turn them into a good old-fashioned double integral, where this will be called P, this will be called Q, and this will be called R. Have you noticed that P, Q, and R are used twice? The PQR that I used to do the curl is not the same PQR that I used. Right, scrolled the wrong place here. That I've used here, right? Different PQR. Well, you plug in all the values. If you're thinking about who is Z, I had to do a whole load of work, which I zoom by. We need to know what Z is, the formula for the surface that we've got, because that is the Z that gets used in replacing any Z's that are left over in the double integral, and it's also the Z that you need to find dz by dx. So if you take these 3 points, this entire chunk of working is me just finding the equation of the plane. And what you do is you find A to B to A to C, you get the normal vector, you then use this version, and you get that answer. So back to our guy. Oh, we know integral. We know P, we know Q, we know R. We know what Z is, so that's how I managed to get these fellas. And the answer becomes that. And the double integral, you don't need to be told y equals, is from 0 to 1 and 0 to 4. Right, remember those 4 points, if you put them on the floor, end up being a rectangle? That's a rectangle. Now, if you take Z, because it's left over, and you replace it by a quarter y, that disappears and becomes just another value of y. Tidy it up, you get this guy. And this fella, eventually, is 15 halves. There's still a little bit of work, but you can do it. And for completeness sake, we're done.